Hello everyone, welcome to the first day in this journey to become a data scientist. So today we'll learn about what is data science and how statistics is important in data science. So to put it simply, data science is like being a detective for data. Imagine you have a huge collection of information, and this could be numbers, text, images, or anything else that can be stored in a computer. But just having all these data doesn't mean much if you don't know how to make sense of it. And that's where data science comes in. At its core, data science is the field that combines tools from statistics, mathematics, and computer science to analyze data, to find patterns and make decisions based on those patterns. It's about turning the raw data into valuable insights. So here is a simple analogy. Think of the data as raw ingredients in the kitchen. Just like a chef uses the recipes, techniques, and tools to turn those raw ingredients into a delicious meal, a data scientist uses algorithms, statistical models, and computing power to turn all this raw data into something useful, like predictions, trends, or actionable insights. For example, companies like Netflix use data science to recommend movies and shows you might like based on what you have already watched before. Amazon uses it to suggest products you might be interested in. So data science is what allows these companies to tailor their services specifically to you by understanding and predicting your preference. Now coming to our first topic, that is statistics, why it is so important in data science. So statistics is fundamental to data science because it provides the methods and tools for collecting, analyzing, interpreting, and presenting data. So let's come to the first point, that is data collection and sampling. Why it's important? In data science, we often work with large data sets, but sometimes we only have access to a sample. Statistics helps in designing experiments and surveys to collect data effectively. It ensures that the sample data is representative of the entire population, which is crucial for making accurate inferences. For example, if you're trying to understand customer satisfaction for a product, you can't ask every customer. Instead, you take a sample. Statistical techniques ensure that this sample accurately reflects the broader customer base. Next, we come to data analysis and exploration. Why it's important? Because before diving into complex models, data scientists use statistical methods to explore the data. This includes understanding the distributions, identifying outliers, and detecting patterns. This step is essential to prepare the data for modeling and to gain initial insights. For example, suppose you have sales data over a year. Descriptive statistics like mean, median, mode, which we'll learn about it later, can help you understand the average sales, the variability, and whether there are any unusual sales figures going on. The third is hypothesis testing and inference. Why it's important? Data science often involves making decisions based on data. Statistics provides a framework for hypothesis testing, which allows data scientists to make inferences about a population from a sample. It also helps in understanding the likelihood that a result is due to chance. For example, if you launch a new website feature and want to know if it increases user engagement, you can use statistical tests to compare the engagement metrics before and after the feature launch and determine if the change is statistically significant. Next, we come to predictive modeling. Many data science tasks involve building models to predict future. Statistical methods underpin many of these predictive models. So methods like linear regression, logistic regression, and various machine learning algorithms have all roots in statistical theory. For example, predicting house prices based on various features like size, location, number of rooms can be done using statistical models like linear regression. Coming to the fifth point, in real-world data, there's always some level of uncertainty. Statistics helps quantify this uncertainty and providing confidence intervals and error margins that guide decision making. For example, if a model predicts that a customer will spend around $500 next month, statistics helps you understand the range within which this prediction might vary, such as being 95% confident that the actual amount will fall between $450 and $550. The sixth point is A-B testing. A-B testing is a statistical method used in data science to compare two versions of something, like a website or an ad, to see which performs better. It is a controlled experiment that relies on statistical analysis to draw valid conclusions. For example, an online retailer might use A-B testing to determine whether a blue buy now button leads to more sales than a red one. Statistical methods are used to analyze the results and determine if one button is truly better. Coming to the last part is evaluating models. So after building models, statistics is crucial in evaluating how well they perform. Metrics like accuracy, precision, recall, and F1 score are all statistical measures that help in understanding the model performance. For example, in a classification problem, let's say if you're trying to classify an email is either a spam or a ham, you would use statistical metric to evaluate how many spam emails were correctly identified versus how many legitimate emails were wrongly flagged as spam. Now, since we know the importance of statistics in data science, let's start with the very basics of it. So, statistics can be broadly classified into two types: the descriptive and the inferential. So, the descriptive statistics help us to simplify and summarize large amount of data in a meaningful way. They provide simple summaries about the sample and the measures. Descriptive statistics are the starting point for data analysis. Coming to the inferential statistics, it allows us to make predictions or inferences about a population based on a sample of data. It is about making generalizations from the data we have collected to a larger group of population. Coming to the descriptive statistics, we can broadly classify descriptive statistics into three main categories. The first one is the measure of the central tendency. The second is the measure of variability or dispersion. And the third is the measure of frequency distribution. Now, coming to the measure of central tendency, these measures provide a single value that represents the center point of a dataset. The three main measures are mean, which is the arithmetic average of all the dataset, the median, which is the middle value when the data is ordered in ascending or descending, and then the mode. The mode is the most frequently occurring value in the dataset. Coming to the measures of variability, these measures help to understand the spread of the distribution of the data points in the dataset. Key measures include range, which is the difference between the highest and the lowest value in the dataset, the variance, which is the average squared deviation of the mean, and the standard deviation, which is the square root of the variance, indicating how much individual data points typically differ from the mean. Coming to the third measure of frequency distribution, this describes how often the central data points occur within the dataset. So the key measures include count, which is the total number of occurrences of a specific value, the relative frequency, the proportion of occurrences of a specific value relative to the total number of data points, and the cumulative frequency. So this is the accumulation of frequencies up to a certain point in the dataset. For example, in a dataset of survey responses where the options are male and female and the other, if the data shows that it's 2 males and 3 females and 1 other, the frequency distribution gives a clear view of how responses are distributed. Now, coming to the univariate and the bivariate data analysis. Univariate data analysis focuses on one single variable to describe its characteristics without considering the relationship with other variables. For example, analyzing the average age of students in the classroom without relating it to any other variable. Bivariate analysis, on the other hand, involves the analysis of two variables to understand the relationship between them, such as examining the correlation between the age and the test scores of student. Now coming to the visualization part, visual representations is a crucial part of descriptive statistics. Common visual tools include histograms, which are used to display the frequency of the frequency distribution of the numerical data, and the box plots. This summarizes the data by showing the median or the quartiles and also the potential outliers. Coming to the outliers, outliers are these data points that significantly differ from the other observations. They can skew the results of the descriptive statistics, especially the mean. So if you see, if the outliers are present, this can significantly affect the fit to these lines. Detecting and managing these outliers are essential for accurate data analysis. So that's why methods like box plots or z-scores can help identify these outliers, which can be best analyzed further to determine whether they should be included or excluded from the dataset. Now, what is the main difference between descriptive statistics and inferential statistics? While descriptive statistics summarize the data at hand, inferential statistics go a step further by making predictions or inferences about a population based on a sample of data. For example, a company might use descriptive statistics to analyze past sales, but would rely on inferential statistics to predict the future sales based on that data. Coming to the inferential statistics, it can be defined as the process of using data analysis to infer properties of an underlying distribution of probability. It is used to reach conclusions that extend beyond the immediate data alone, allowing researchers to predict trends, compare groups, and make decisions based on data analysis. Inferential statistics can be broadly classified into two main types: the hypothesis testing and regression analysis. Each type plays a crucial role in analyzing data and making predictions. Coming to hypothesis testing, it is a statistical method used to make decisions about a population based on sample data. It involves setting up two hypotheses: the null hypothesis, which represents no effect or no difference, and an alternative hypothesis, which represents an effect or a difference. Based on the sample data, statistical tests are conducted to determine whether the null hypothesis should be rejected in favor of the alternative hypothesis. But if you don't understand it at this point, do not worry, because we will see practical applications and in-depth inference of hypothesis testing in the next video. Again, hypothesis testing can be of different kinds. First comes the Z-test. It is used when the data follows a normal distribution and the sample size is large, that is more than 30. It tests whether the mean of the sample and population are equal when the population variance is known. Then comes the T-test. It is applied when the sample size is small, that is less than 30, and the population variance is unknown. It compares the sample mean to the population mean. Next comes the F-test, which is used to compare the variances of two populations. It checks whether there is a significant difference between the variances of two samples. And then comes the confidence levels, which is used to estimate the population parameter. For example, a 95% confidence interval suggests if the same population is sampled multiple times, 95% of the time, the parameter will fall within this interval. Coming to the regression analysis, it is a statistical technique used to understand the relationship between variables. It helps in predicting the value of one variable based on the value of another. The most common form is linear regression. which models the relationship between two variables by fitting a linear equation to the observed data. Some examples for inferential statistics suppose a researcher wants to estimate the average height of students in a large university. Instead of measuring every student, the researcher randomly selects 100 students and calculates the average height. Using inferential statistics, they can make a prediction about the average height of the entire student population. Another example is that a market analyst wants to determine the effectiveness of a new advertising campaign. By analyzing the responses of a randomly selected sample of customers, the analyst can infer whether the campaign is likely to be successful among this entire customer base. So this is it for today. It gives you an introduction to the type of statistics and why is it important in data science. And tomorrow we'll see some more in-depth analysis on the hypothesis testing and also on the central limit theorem and all other statistical phenomena. So thank you for watching and please stay tuned for day 2. Thank you.